Hello everyone. In this video we are going to learn the influence line diagram for a simply supported beam with overhang. Now already we have learned how to draw the influence line diagram for reaction at A, reaction at B, and shear force and bending moment for a given section. Now if you see the influence line diagram for reaction at A for simply supported beam. So at support A the ordinate is 1, where at support B the ordinate is 0. If you see the influence line diagram for reaction at B, support B, at support B the value of ordinate is 1, whereas at support A it is 0. Okay. Now if you see the influence line diagram for shear force at the given section. Now here we are given the name to the section as C. Okay. Now at the section there are two values. One is A by L and another is B by L. And if you take the addition of these two ordinates, that is A by L plus B by L, that value is equal to 1. Okay. Now if you see the influence line diagram for bending moment at a section C, now at the section the value is AB upon L. Okay. So this is the influence line diagram for reaction at A, reaction at B, shear force and bending moment at the given section C. Now we'll see the influence line diagram for a simply supported beam having an overhang. Now if you see this figure, in this figure at A and B the beam is simply supported, whereas on the left hand side of this simply supported beam a overhang is there, that is AC of length C, and on the right hand side of the simply supported beam the another overhang is there, BD, which is of length D. Okay. Now here the section is given at E, which is at a distance A, small a from support A, and distance B from support B, and A plus B is equal to L. Okay. Now here we have considered the unit load, which is at a distance X from support C. Now here we have to draw the influence line diagram for reaction at A, reaction at B, and shear force and bending moment at the given section E. Okay. Now we'll see the first, that is influence line diagram for reaction at E, support E. Okay. Now first we have to draw the influence line diagram for simply supported beam, that is AB. Now we know that at support A the value of ordinate is 1 and at support B the value is 0. Okay. So this is the influence line diagram for simply supported beam. Okay. Now then you have to produce this line, influence line, drawn to cover the overhang portion. Now here this line is extended up to support C, and here on the right hand side this line is extended up to support D. Now here you have to find out this ordinate. Now we don't know what is the value of this ordinate, so we'll call this as x1, this ordinate as x1, whereas we'll call this ordinate as x2. Call this ordinate as x2. Okay. Now to find out this value of x1 ordinate and x2 ordinate, we have to find out by the principle of similarity triangle. Okay. Now for that we'll consider two triangles, one this triangle and another these two triangles. Okay. Now if you see, this 1 is equal to x1, so 1 is equal to x1, whereas the length AB, which is L, okay, which is equal to this length CB. Now length CB is nothing but C plus L, So L plus C. Okay, now here we have to find out this ordinate. So the x1 will be equal to L plus C upon L. So the ordinate x1 is equal to L plus C upon capital L. Same way, to find out the ordinate x2, we will consider this triangle and this whole triangle. Okay, now this ordinate 1 is equal to x2. So 1 is equal to x2 and the length AB, which is L, which is equal to length PD, that is small d. So here we want the value x2. So x2 is nothing but d upon L. Okay, so we know this value of x1, now x2, and this is the influence line diagram for reaction at support E. Okay, now the same procedure is adopted or followed to draw the influence line diagram for reaction at support B. First, draw the influence line diagram for simply supported beam AB. Produce the influence line drawn to cover the overhang portion on the right hand side, that is BD, as well as on the left hand side, that is CA. Okay. Now here this line is extended up to support D, whereas from support A the line is extended up to C point. Okay. Now here you have to find out this ordinate. Now we'll name this ordinate as x4. Okay. And we'll name this ordinate as x3. Now to find out x4, so we'll consider this triangle, whereas this triangle. Okay. Now 1 will be equal to x4. So 1 will be equal to x4. Now length AB, which is L, which is equal to length AC, which is C. So L will be equal to C. So from this we'll get the value of x4, that is C upon L. Same way, to find out the ordinate x3, you have to consider this triangle and another this triangle. Okay. So see, 1 will be equal to x3. Okay. Then 1 will be equal to x3. The length AB, that is L, which is equal to length AD, which is L plus D. So L plus D. So from this we'll get the value of x3. Okay, so this is the influence line diagram for reaction at B. Now next is, we'll draw the influence line diagram for shear force at section E. Again we have to draw the influence line diagram for the simply supported B. Okay, we know that at the section at support A and support B the value is 0, whereas at the given section here the value is A by L, whereas it is P by L. Okay. Now, produce the influence line drawn to cover the overhang portion up to the point C, whereas up to the point D from the both support. Okay. Now here we have to find out this ordinate. Okay. Now we'll name this ordinate as x5 and this ordinate as x6. Okay. Now to find out ordinate, we'll consider this triangle and this triangle. Okay. Now this x5 will be equal to A upon L. So A upon L is equal to x5. Okay. Then this length AE, which is A, which is equal to length CA, which is small c. So A is equal to C. So value of x5 is C upon L. So value of x5 is equal to C upon L. Now to find out x6, we consider these two triangles. Okay, so B by L will be equal to x6. Okay, and length EB will be equal to BD. So EB is nothing but B and BD is nothing but small d. So we'll get the value of x6, that is D upon L. Now we'll draw the influence line diagram for bending moment at section E. Again we'll draw the influence line diagram first for the simply supported. Produce the influence line diagram to cover the overhang segment, okay, on the both side. Now we'll find out this ordinate. Now we'll call this ordinate at x7 and this ordinate as x8. Okay. Now to find out this ordinate x7, we'll consider this triangle, two triangles. Okay, now x7 will be equal to AB upon L, and this length AE will be equal to length AC. A is nothing but A and AC is nothing but C. So we will get the value of x7, that is CB upon L. Now to find out the ordinate x8, we will consider these two triangles. Okay, AB upon L will be equal to x8 and EB will be equal to BD. EB is nothing but small b and BD is nothing but D. So we'll get the value of x8. So in this way we have seen how to draw the influence line diagram for simply supported beam having the overhang on both the sides. So it is also called as double overhang simply supported beam. Okay. Now the influence line diagram for single overhang beam. Okay. Now if you see in this figure, AB is the simply supported beam. On the left hand side of this simply supported beam, there is an overhang of length C. Okay. Now in this case again you have to draw the influence line diagram for simply supported beam and then extend this line for the overhang portion. Okay. And then find out this ordinate. Already we have seen in the last slide. Okay. So this is the influence line diagram for reaction at A. Okay. Same way, this is the influence line diagram for reaction at B. First you have to draw for the simply supported beam and extend the influence line for the overhang portion and find out this ordinate by considering these two triangle, which is equal to C upon L. Okay. Now influence line diagram for shear force at section E. Again draw it first for the simply supported. Okay. Extend the influence line diagram for overhang portion. Find out this ordinate by considering the principle of similarity of triangles. Okay. Where we will get this ordinate. Okay. Then influence line diagram for bending moment at section E. Again first draw for simply supported beam, extend for the overhang portion, find out the ordinate. Okay. Now this was a influence line diagram for single overhang beam on the left hand side. Okay. Same way, this is influence line diagram for single overhang beam on the right hand side. Okay. Now we'll consider a numerical. A beam ACDB is as shown in the below figure. Find the reaction at support, shear force and bending moment at 4 meter from support C using influence line diagram. Okay. So this is the beam ACDB. The beam is simply supported at C and D. Okay. And the overhang CA of length 5 meter, which is equal to small c, and overhang on the right hand side of the simply supported beam of length 4 meter, and the length of the simply supported beam is 10 meter. Okay. Now here they have given the section E, which is at 4 meter. They have mentioned 4 meter from support C, 4 meter from support C, and this value is equal to small a. Okay. So 10 minus 4, so the value of B, that is from support D, will be equal to 6 meter. Okay. Now they have told to find out the reaction at support. So reaction at support means you have to find out reaction at support C, reaction at support D, as well as we have to find out the shear force and bending moment at given section, that is at E. Okay. Now we'll you have to first draw the influence line diagram for reaction at C. Already we know how to draw the influence line diagram for reaction at C. Okay. First draw for the simply supported beam. Now at C, the value of the ordinate will be equal to 1, and at support D the value will be equal to 0. Okay. Extend for the overhang portion and find out this ordinate. Okay. Now here by considering the similarity of triangles, we have find out this ordinate. After finding out this ordinate, you have to find out the ordinate below the point load. Okay, now here you have to find out the ordinate below 45 kilonewton. You have to find out the ordinate below 35 kilonewton. Okay, so ordinate below 20 and 30 already I have calculated. Okay, now to find out the reaction at C. Okay, now as here all are the point loads. Okay, so point load multiplied by the ordinate in the influence line diagram. Now here the point load 20 into the ordinate is 1.5 plus second point load is 45 into the ordinate 0.7. Next point load is 35 into 0.40. Now here this ordinate is on the negative side, so it is minus. Point load is 30 kilonewton multiplied by 0.4. Okay, now if you solve this, we'll get the reaction at C is equal to 60.50 kilonewton. Okay, now next is the reaction at D, reaction at support D. Okay, first draw the influence line diagram for simply supported, extend it for the overhang portion, find out these ordinates. Okay, already we know this value C by L and L plus D upon L. Okay, now find out the ordinate below the point load. Okay, after finding out its ordinate, okay, now here the ordinate below 20 kilonewton is on the negative side, so here minus 20 into 0.5 plus 45 multiply the ordinate is 0.30, then 35 into the ordinate 0.60, then 30 into the ordinate 1.4. Okay, if we solve this, we'll get the reaction at D as 66.50 kilonewton. Now next you have to find out shear force at the given section E. Draw the influence line diagram for shear force at E. First draw for the simply supported, then extend for the overhang portion. This value we know C by L, this is D by L, here the value is A by L, here it is B by L. All the values we know here. Okay, now after finding out of this ordinate, find out the ordinate below the point load. Okay, then here shear force at E is nothing but ordinate the point load 20 multiplied by the ordinate 0.5, then this is on the negative side, so minus 0.3 into 45, the next one is 0.40 into 35, again this is on the negative side, so 30 into 0.4. If you solve this, we'll get the value minus 1.5 kilonewton. Next, find out the value of bending moment at the section E. Okay, again first draw for the simply supported, extend for the overhang portion, find out the ordinates. Here it is BC by L, here it is AD upon L. Put the values of AD upon L. Okay, here it is 1.6, here it is 3. Find out the ordinate below the point loads. Okay, then here the ordinate is on the negative side, so minus 3 into the point load 20. Here the value of the ordinate is 1.8 into the point load 45. Here the ordinate is 1.6 and the point value of point load is 35. Here the ordinate is on the negative side, which is 1.6 minus 1.6 into the point load. Here the point load is 30. Point load is 30. Okay, it is hidden below this. So here bending, if you solve this, we'll get the bending moment at section E, that is 29 kilonewton meter. Okay, next numerical. Two wheel loads 200 kilonewton and 80 kilonewton spaced 0.8 meter apart roll on the girder as shown in the figure. They are told to find out the maximum positive and negative shear force that can occur at the section E. Okay. Now here first you have to draw the influence line diagram for shear force at the given section E. Okay, we know the nature. Now we know this value C by L. Here it is A by L, B by L, D by L. We know the value of C is 2 meter, D is 3 meter, A is 1.5 and B is also 1.5. The length L is nothing but A plus B, which is equal to 3 meter. Now we put here value C upon L. C is 2 upon 3. The value is 0.67. Here it is D upon L. Value of D is 3. L is 3. So this ordinate is equal to 1. Okay. Now here it is A upon L. Value of A is 1.5. L is 3. So it is 0.5. Here B upon L. So 1.5 divided by 3. The value is 0.5. Okay. So this is the nature of influence line diagram for shear force at E, as well as the values of ordinates. Okay. Now they have given the two wheel loads 200 kilonewton and 80 kilonewton, which is placed at 0.8 meter, and we have to find out the maximum positive shear force. Okay. Now if you observe this influence line diagram for shear force at E, okay, so here we have to see the positive shear force diagram. Okay, this is the positive shear force diagram and this is the second positive shear force diagram. Now you have to observe the ordinate now. Now here the ordinate is 0.67, but here the ordinate is 0.5. So below the point load, the ordinate should be the maximum. So here as the ordinate is maximum, so 200 kilonewton should be placed at point C. Okay, and on the right hand side at 0.8 meter you have to place the another point load, that is 80 kilonewton. Okay, already we have found out this ordinate. Now we have to find out the ordinate below the 80 kilonewton by considering these two triangles. Okay, now this 0.67 will be equal to this ordinate X, and this length CA will be equal to this length. Okay, that is 2 will be equal to 1.2, and if you solve this, we'll get this ordinate as 0.4. Okay, now as we know the ordinate and we know the position of load for the maximum positive shear force at E, so we can find out the maximum positive shear force. Okay, so here point load is 200 multiplied by the ordinate, so 200 into 0.67, so 80 multiplied by 0.4. So here we get the value. Now here the two wheel loads are given. So any wheel load can be the first or this second. It is not that 80 should be first or 200 should be first. But here whatever the values of shear force that we are getting, it should be the maximum for positive shear force and maximum for negative shear force. Okay. So in this way we can find out the maximum positive shear force. Now next they are told to find out the maximum negative shear force. Okay. Now if you see here, this is the diagram on the negative side, whereas this is the second diagram of the shear force on the negative side. Now if you observe the ordinate, here ordinate is 0.5, whereas here the ordinate is 1. Okay. As we know that below the point load the ordinate should be maximum. So the 200 kilonewton load should be placed at point D, and at 0.8 meter the second point load or wheel load of 80 kilonewton is placed. Okay. Now below this you have to find out this ordinate. So here you have to find out this ordinate by considering similarity of triangle, this big triangle and then this triangle. Okay, so the value we get is 0.73. Okay, now this is the position of load for maximum negative shear force at section E. Okay, as we know the ordinate, we can find out maximum negative shear force. So here both the ordinates are on the negative side, so it will be minus 1 into 200, the intensity of load, and 0.73 into the load 80. Okay, if we solve this, we get the value of maximum negative shear force as minus 258.40 kilonewton. Now next numerical, two wheel loads 200 kilonewton and 80 kilonewton, space 0.8 meter, roll on the girder as shown in the figure. Find the maximum positive and negative bending moment that can occur at the section E. Okay, again first we have to draw the influence line diagram for bending moment at section E. Okay, we know the nature of influence line diagram for bending moment at section E. Okay, now find out this ordinate CB upon L. The value of C is 3 meter. Okay, value of B is 3 meter. So 9 divided by L, that is 6. So we get this value as 1.714. We know this value AB upon L. 3 into 3, 9 divided by 6. We will get this value. Okay. Same way you can also find out this value AD upon L. Okay, put the value and we will get this ordinate. Now we have drawn the influence line diagram for bending moment at E. Now we have to find out the maximum positive bending moment. Okay. Now here we have to see which diagram is on the positive side. Okay. Now here the ordinate is maximum at the section. Okay. So 200 kilonewton will be at the section. Okay. And this point load, it is 80 kilonewton, we can place on the right side or left side, as here the length on the both side is same. So we can place it on the right hand side or we can also place it on left hand side also. Okay, the ordinate will be the same. Okay, so maximum positive bending moment. So here ordinate is 1.714 multiplied by 200 plus 1.63 into 80. So we get the value 473.20 kilonewton, and this is the position of load for the maximum bending moment at section E. Now next we have to find out the maximum negative bending moment at section E. Okay. Now observe this influence line diagram on the negative side. Okay. Now if you observe here the ordinate is maximum, that is 1.714, whereas here the ordinate is less. Okay, so 200 kilonewton will be at point C, and at point 8 meter the 80 kilonewton load will be there. Okay, if we find out this ordinate, the value is 1.26. Okay, and this is the position of the load for the maximum negative bending moment at E. Okay, so minus this is on negative side, so minus 1.714 into 200. Again this is minus 1.26 into 80. So we'll get the value minus 443.6 kilonewton meter. Okay. Next numerical, find the maximum positive shear force, maximum negative shear force at the given section E. Now a UDL of 80 kilonewton per meter may occupy any position on the girder CABD. Now a beam CABD is shown as in the figure, where the overhang on the left hand portion is of 3 meter, on the right hand portion it is 2 meter. The singly supported beam length is 7 meter. Section E is at a 3 meter from support A and 4 meter from support B. Okay. Okay. Now first you have to draw the influence line diagram for shear force at the section E. Find out this ordinate C by L, A by L, B by L and D by L. Already know this value. Okay. Now here a UDL of 80 km per meter may occupy any position on the girder. Now here they have not given the length of this UDL 80 kilonewton per meter. Okay, but they have mentioned that it may occupy any position on the girder, provided that we should get the maximum positive shear force and maximum negative shear force. Now if you see, to find out the maximum positive shear force at section E, you have to see the positive shear force diagram, okay, at the section E. So CA and EB. Now on this portion you have to place this 80 kilonewton meter load. Okay. Now, so in this way you have to place the load to find out the maximum positive shear force at section E. Here E is remaining. Okay. Now here it is, as it is UDL. So below the UDL you have to find out the area. Okay, so you have to find out the area of this triangle, multiply by intensity of the load. Okay, so here it is. So area of this triangle, 1/2 base is 3 meter and height is 0.43. So 0.5 into 0.43 into 3, and the loading is 80. So the next point load, next this figure, that is 1/2, base is 4, this ordinate is 0.57 into the 80. Okay, so if we solve this, we'll get the maximum positive shear force at E. Okay, next maximum negative shear force. Okay, so this is the negative diagram. So on this portion you have to place the UDL of 80 kilonewton meter. Okay, so here they are, the position of load for maximum negative shear force at section E. Now below this again the area is triangle. Okay, ordinate already we know here. Okay, so here it will be minus 1/2, length is 3, height is 0.43, multiply by the intensity of load 80. Okay, next this triangle 1/2, then length is 2, height is 0.28 into the intensity of loading 80. So we get the value as minus 74 kilonewton. Okay. Next numerical, find the maximum positive and maximum negative bending moment at section E. A UDL of 80 kilonewton per meter may occupy any position on the girder. Okay, as shown in the figure. Okay, the girder is CABD. It is CABD. Okay. Now here C is equal to 3 meter, A is equal to 3 meter. That means section E is at 3 meter from support A. Section E is at 4 meter from support B. The overhang on the right hand side, it is of length 2 meter, and on the left hand side it is of 3 meter. Okay. First draw the influence line diagram for bending moment at the section E. We know this value CB upon L, AB upon L, AD upon L. Put this value, we'll get these ordinates. Okay. Now they are told to find out maximum positive bending moment at section E. Okay. Now here the UDL is of length UDL of intensity 80 kilonewton per meter. The length is not given, but they are told to find out the maximum positive bending moment. So the length will be equal to this positive diagram. Okay, so that is AB. So this is the position of load for maximum positive bending moment at section E. Okay, now here the figure in the influence line diagram, below the UDL is a triangle. So maximum positive bending moment at E will be 1/2 base. Here base, this total length is L, which is equal to 7 into the ordinate 1.714 into the intensity of UDL is 80. If we solve this, we'll get this value. Okay. Now next they are told to find out maximum negative bending moment at the section E. So this is the negative diagram. So you have to place the UDL over this portion as shown in this figure. Okay. Now below this UDL, the nature of the impedance line diagram is a triangle. Okay, so here minus 0.1/2, here the length of CA is 3 and the height of the ordinate is 1.714, into the intensity of the UDL is 80. Here 1/2, the length is 2, height is 0.85, intensity of UDL is 80, and if we solve this, we'll get the maximum negative bending moment at the section E. So thank you very much.